It's a very exclusive group. Those of you without the invites were all told to leave. So thank you guys for keeping this hush-hush. So basically, kind of to play off what Klaus said, is that I'm been doing a lot of architectural research, so stuff that happens either below the operating system or even at the firmware level or the hardware level. And I found that a lot of people are starting to get into this. I've seen a lot of cached side channel attacks, and the row hammer research got more people interested in this kind of low-level area. And I've gotten a lot of emails almost every week, invariably with very poor English, asking me questions about how to fix a bug in my code that I wrote back in 2008. So basically my goal is to reflect back on the last few years and figure out how I can accelerate other people from doing this so that they can be better at doing this low-level research, which I find to be very, very interesting. So as noted, this is a very different format from the usual talks, so feedback is welcomed. So Klaus was very happy, and very popular tweet. I don't know if you saw this. Has, I don't even know how many retweets, but he came all the way from his house in Luxembourg just to see me talk. So clearly I've got a pretty strong fan base right there. It's very easy to tweet fake things and create them. So if you're ever looking for, you want One Direction to tweet at you for your kids to impress them or whatnot, it's quite straightforward. So I've already talked briefly that I'm not going to talk about any really cutting edge new research, just more about how ways that you guys can do your research more efficiently. And then also the slides are quite wordy and verbose, not because I like reading off my slides, but so that if you guys can come back to these later, they'll be published and you have a place to jump off from. So real quick, I work in Denver, Colorado in the US. I work for, but don't speak for, Assured Information Security. We're a small, 200-person research firm. That's all we do. I lead the low-level computer architectures research group, and as I said, I'd like to play in Intel privilege levels less than or equal to 0. So what is a privilege level? So in x86, which is the Intel system that most computers here are running, other than the iPad probably, back in the old days when they first came out, they had no separation of privileges, and so any malbehaving or misbehaving application could overwrite kernel memory or do whatever they needed to, so that was kind of a bad thing. And so the 386 added protected mode and separation. So now one misbehaving application really can't trash the kernel or other applications. Officially, there are designated rings 0 for 3, with 0 being the most privileged and 3 being the least. And then unofficially, there's also -1, 2, and 3. So when you're setting out to do some architectural research, you need to figure out what ring to play in, because typically the higher the ring or the less privileged it is, the easier it is to start getting access to it. So it's really nice and easy to write a program in user space because you have all the debugging tools, you have a compiler. If it crashes, it doesn't blue screen or triple fault the box. If you have to write something in OS level or system management mode, you really have no idea what you're doing, and the debugging tools for that is very, very expensive. So you first want to figure out what level you need to play at, and then figure out how to get there as easy as possible. So virtual memory, I talked about this very briefly at my lightning talk in about maybe 10 seconds. One of the more powerful features for OSs to basically control and master their processes is the concept of virtual memory and paging. Basically, more privileged code can isolate and then manage the paging, the view of memory for less privileged processes. So that could be an operating system managing applications, or a hypervisor or a VMM managing operating systems. So real quick, the CPU has a register that I talked about yesterday in my lightning talk, CR3, which has a pointer to the page tables. And whenever you access a pointer, you're going to go through, you're going to look up that directory, you're going to find that. They might have a pointer to a page table, and it's going to go find that, and then eventually it's going to get the address to look up. So kind of slow, but pretty impressive and very powerful. And that's why when you write a user space application, you could have 2 applications that have the same pointer that's pointing to different memory because they have different page tables. Memory access is quite slow, and you can see that was only like 3 or 4 lookups for a single byte of memory. If you were on a virtualized system and you had 64-bit, it could be, I think, upwards of 9 memory translations and access to memory, which is very, very, very slow. So basically, the CPU defaults to always accessing cache, and cache will save a lot of time, And it has a caching hierarchy as well, because cache is quite expensive, and the bigger it is, the longer it takes to search through it. So usually they like to kind of have this cascading hierarchy of L1, L2, and then L3 as a shared resource between different CPU cores, which been done some very interesting side channel research in that lately. How memory is cached is a very difficult kind of combination between control register bits, bits and paging structures, and then some other registers called the MTRRs. It's some extra things if you're interested. So new CPUs have something called CAT, cache allocation technology, which allows you to kind of hard allocate certain regions of cache to certain VMs or certain cores, try to help give more performance to certain systems. And then another one was Invisible Things Lab showed an SMM attack, or system management attack, where since the controller, the memory controller, determined if you could access system management mode, and the CPU basically says, I'm in system management mode, but because the CPU talks directly to the cache, if you change system management mode to be cacheable, it would access the cache rather than going out to the controller hub, memory controller hub, and then you could actually break into system management mode very, very easily. So you can now lock MTRRs for certain regions. So there's also a cache for these virtual to physical address translation. This has been most of my research over the last few years has been into TLB. So translation look-aside. Logically, if you were to look at the Intel manuals, there's really kind of one that just give it a virtual address and a physical address pairing, and it will save it for later. If you actually were to take an X-ray of a CPU, you'd see that there are between 2 or 3. There's one for instructions, one for data, and then one that can be shared between them. And this is a very straightforward diagram of you access memory. If it's already cached, great. If not, go through and then cache it. Then the IDT and IVT, these are the interrupt vector and interrupt descriptor tables relatively, or respectively. This is kind of the main mechanism for both the operating system or a hypervisor to respond to hardware events. So you plug in a new USB stick, or your hard drive is finished loading off a page of memory or a block out of the hard drive, and it can give you an interrupt so you're not constantly polling on that device. The IDT is in protected mode and the IVT is in real mode. We'll talk about that a little bit later. Basically, you fill a table in memory and you pass a pointer to that into a certain register. And then this is how you can jump from one privilege level to another. So if you're going to make a system call, this is how you kind of use that. And so I believe it was int 8 used to be the one that you could use to switch on some operating systems. Virtualization, this is the first unofficial ring, ring minus 1. So I'm sure you guys have all heard of at least Zen or VirtualBox or KVM. Basically the same thing that an operating system can do to applications, a hypervisor can do to operating systems. So originally, before they added hardware support, it was kind of in a hacky way where you were doing dynamic binary translations, or you're kind of pushing the operating systems into a slightly lower ring, but not the full lower ring. But now you have CPUs, most every CPU has unmodified OS support with something called VTX. So that basically just allows you to set up applications that are operating systems and then manage them quite simply. If you want to preempt the operating system, one way to do that is by hooking things really early. A lot of the modern operating systems do a really good job of preventing patching. So you might have heard of PatchGuard. So one way you can get in there if you want to instrument the operating system or do something else is to preempt that through hooking the boot process. So a system starts up in 16-bit real mode, kind of like that kind of fail MBR rootkit. And you hope that they've copied and changed the 16-bit to 32-bit properly, because it needs to support backwards compatibility to DOS, and that's what legacy BIOS runs in, is a 16-bit mode. But every system these days is more modern. It has something called UEFI, the Universal Extensile Firmware Interface, where basically it runs almost like a light operating system shell in protected mode for extra performance and extra features, and then it can do a whole bunch of cool stuff there. So depending on what system you're on, you're going to have to hook BIOS or hook UEFI. So BIOS, basically it loads it off of a ROM or a flash, and then it initializes the system as well as the IVT. It configures system management mode, and so that's what system management mode is there for, is for BIOS to be able to persist through the boot process, and then hopefully locks it up. In the past, it used to not do that, and so it was very nice to play in system management mode very easily. It then executes PCI option ROMs to configure these hardware devices. So if you have a RAID controller, your BIOS might not know how to configure and talk to that RAID controller directly. So it'll ask the RAID controller, hey, hook the IVT process for loading blocks off a disk, and you set yourself up and then pass it back to me. And then finally, obviously, the bootloader gets called, and then the bootloader has basically an API through this IVT to call certain functions, some of which are designed to be hooked by the operating system for the BIOS to tell them, hey, we've gotten to this part of the boot process, or hey, this device is ready for you. With EFI, basically, you're really quickly loading into protected mode, and then it configures identity map page table. So that means a virtual address is just mapped directly to the same physical address, and then it has an IDT rather than IVT. It configures system management mode, which is called runtime services, and again, hopefully locks it. There's been a lot of work in the last couple of years by, well, there was the Legba core guys, now they're Apple, doing exploitation of this because the source code and the reference implementation is open, so you can just throw something like Coverity or some other form of fuzzer at it, or a static analysis tool, and you can actually find vulnerabilities. And then all your BIOS vendors do is they copy that reference implementation, change out the logo for theirs, and then they sell it again. So interesting places for vulnerability research as well. This one also executes PCI option ROMs, but it's in an environment called the DXE, the driver execution environment. And then basically it runs a PE file, which could be either an application that runs and then terminates, or it can then load an operating system, etc. And it passes a system table, which is basically an array of function pointers for all the services that it provides to the next application being run. So if you wanted to hook the boot process, basically you figure out if you're on BIOS or EFI. So you want to start really easily with like a bootloader skeleton. So that could be even simpler than grub, basically. You want to hook the boot process and then basically run the boot process. So you can hook IVT really easily. So if you wanted to do that, you could just basically hook any IVT entry, put yourself in memory somewhere, and then you'd be able to get, kind of man in the middle these OS to BIOS calls. In EFI, you can basically just develop an application that gets run and then use the EFI services load image and then start image to start the operating system. But you can change the pointer. So you could basically hook any function pointer from the boot services, and then the operating system, when it's loading, will call you first. So you can kind of get really early access to how the EFI bootloader is running for your operating system. As I mentioned before, PatchGuard makes interrupt hooking quite a bit more difficult, so XP or 7 is probably preferable unless you want to go up the hypervisor route, which I'll talk about a little bit later. When you are hooking a hypervisor or the interrupts, you want to make sure your compiler doesn't destroy register states, because you're not necessarily setting up the proper frame pointer and you're not saving the variables the same way. You can also configure a hypervisor to trap on any kernel level interrupts. And so it might actually be easier, and I think it actually is, to write a hypervisor to trap on certain stuff. And I'll talk about that a little bit later, rather than trying to patch kernel. So here's a couple examples for this stuff. So if you were to trap page faults, which is what the Shadow Walker memory hiding rootkit by, I think it's 2005, 2008, by Sherry Sparks and Jamie Butler, basically they hooked the page fault handler to figure out if the virtual address was being accessed for purposes of reading data. It would pass it to one place, which was probably the unmodified Windows kernel. And if it was being accessed like as a call or a jump for data or for instruction fetch, it would point it to a rootkit. And so an antivirus or a anti-rootkit system would be scanning memory, and when it reached those pages, it would get directed to the benign official Windows version. But then if you actually jumped to it, or when it got scheduled in, it would run the malicious code. Again, you have the TLB there, so you might not necessarily actually have to trigger the page fault, so you got to invalidate that if you want to re-trigger that fault. The general protection fault is another one that's pretty common for hooking. That was used by the PAX GR security guys to emulate the no execute bit before it existed in hardware. Basically, if the mapping is valid but the permissions are wrong, it'll trigger that fault. And so what they did is they basically said that all the user space applications that were being protected could only be accessed in ring 0, even though they're being run in ring 3. And if the type of access was a data access, they would set the bit to allow it, prime the TLB, and then reset it without invalidating that TLB, essentially splitting out the data TLB and the instruction TLB, so that the CPU had a different view of memory depending on whether or not it was trying to execute code or read code. And so basically they were able to enforce the no execute bit way back in the day before that was a hardware feature at very minimal impact. Another one we're seeing a lot now is performance counters. Basically, Intel provides a whole bunch of registers out there that you can use to see different, introspect into how the CPU is running, to tune your code if you're writing something very performant, or they've been kind of misused lately or used more creatively lately to be able to do all sorts of interesting things. So the nice thing is usually they're accessible as the kernel mode, but they have APIs to export them of varying quality. Just some examples is you can track the last branch a process made. So if you wanted to kind of do some form of ghetto control flow integrity, you can kind of see to make sure the branch was actually something where it should be. You can do the cache miscounter, which was used by some folks at Black Hat last year to detect rowhammer attacks because it was causing that cache failure rate to go sky high. They could just really quickly read that register and say, all right, someone is trying to rowhammer us. We should take precautions. And then another one is if you're looking for a research topic, you can actually get the number of misses in the TLB, and similar to that rowhammer, you could probably detect a TLB splitting attack based on how many misses the TLB has compared to normal operation. So if you wanted to do more of this control flow integrity or kind of figure out what the program is doing, you can do branch tracing. So originally it was very low overhead but low power, so you can only record a certain number of last branches, and then they came out with something called BTS, which is a much higher amount but a really high overhead. It was like cripplingly slow. The new Skylake and newer CPUs have something called Intel PT, that basically you have a ring buffer to some other process, and it basically can track all of the processor's behavior with a certain application. So lower overhead and much higher power. So that I think is going to be very interesting to see, because now you can start instrumenting, fuzzers or static analysis or symbolic execution far more quickly because of the hardware analysis capabilities they put in there. And if you're interested, there's a GitHub link to Intel's code for that. So a VM exit, so similar to interrupts, but the hypervisor gets notified when certain events occur. Some of them are mandatory to trigger a VM exit, and some are configurable. So one way, if you're trying to figure out if you are being run in a hypervisor and you're not planning on it, you can call an instruction like the CPU ID, which will always trigger a hypervisor, and that'll basically force that hypervisor to fault and take a lot longer. If you don't have another feature called VPID, your TLBs will be flushed and then it comes back. And then there's a few interesting events that I think are curious, like the hardware random number generator is one that you can be notified of if you're a hypervisor. So if you have a hypervisor and you want to play some crypto tricks on people, that's a good one. Any moving to the control registers, MSRs, CPU ID as I mentioned, and then any IO to hardware devices. Timestamp counter, if you want to try to detect if you're being virtualized, you can actually set it up to automatically skew the timestamp counter to hide the amount of time the processor is taking to run the hypervisor. And then also you can single step, obviously. EPT faults, again, analogous to what you see in page faults, but they again go to the hypervisor and allow a hypervisor to manage the OS's view of memory. You can also just trap on the page fault as well. So that's what I did, and I'll talk about that a little bit later, to be able to not fight with the operating system's memory manager. System management mode, again, we're not going to spend too much time on this. It's ring -2, again, unofficial. Basically, it was an old version or an old kind of mode like the appendix in people's bodies. It's kind of not really there as much for much purpose anymore, but basically back in the day when chipsets were very difficult to control without ACPI, they allowed you to put in privileged code transparently to the operating system, so you could handle thermal events, you could turn the system off. Back in the day, you remember he says it's now safe to turn off your computer. That was because it didn't necessarily have the code to actually turn off the power supply. A lot of interested research in this area, but it's now protected, and now they use it for EFI. It's the highest privilege on the system, minus one kind of caveat. It has full access to system memory, and then other than side channels, it's very difficult to detect its execution. We're gonna skim through a lot of this. I already talked about that caching attack. So it's entered through another type of interrupt, aptly named the system management interrupt, SMI. It'll handle the interrupt and return, and all of the hardware will actually save all of those registers and flags, so it's a really stealthy mode of execution. And you can actually run a second hypervisor in system management mode, so you can have two of them running kind of in concert at the same time, and that's called STM. There's an open source reference implementation, but I've never seen it deployed. So to put all this in context, now that you have a lot of alphabet soup for acronyms, we're going to go through kind of a quick case study and then how I solved it in the past, which was suboptimal, and now how I would do it now. And if you're trying to do something in this field, maybe how you could do it to speed up your process. So what I wanted to do is the TLB splitting that was done in Shadow Walker and the GR security, but on more modern CPUs where they now have a second layer STLB, which is basically is to the right of those highlighted in red. There's another one with bidirectional data flow. So what I had to be able to do is to trap on memory accesses, differentiate whether or not it was a code instruction fetch, manage memory without the operating system interfering. So Windows XP, you could pretty much do whatever you wanted with the memory and the page tables, and it would not care or notice. Windows 7 and now and newer are obviously much better. Minimize performance impact, and then I had no knowledge of the source code or access for what the programs that I was kind of mucking with. So I needed a thin hypervisor that supported a modern operating system. It had to have a VPID, which is the tag TLB entry, to prevent it from flushing every time the exit occurred. And then I needed to be able to use structures for EPT, which had a more granular execute-only permission that allowed me to kind of enforce that separation between data and code, even with an STLB. And I didn't realize I needed this until I was already under contract with DARPA under a cyber fast track program for MUDGE. And I didn't realize this until about maybe a month and a half into a 4-month effort, and I had to deliver it. So I had to do something really fast. We do a lot of research with Zen and KVM, but it's way too big of a code base to start trying to change. So I needed something really quick that I could kind of do so I could work on my hypothesis and not trying to reverse engineer and come up to speed on a 150,000 line hypervisor. So I started with a kernel driver for Windows 7 before I realized that I needed to not have a kernel driver. I ran into these issues and Windows 7 would blue screen. So I had to switch. So I found a rootkit on rootkits.com that was a hypervisor rootkit. Cleaned it up, added and debugged support for EPT and VPID. So back in the day, like it was like 3 people in the world that had ever implemented VPID and EPT, and I had to find them from the Zen mailing list and email them questions about why it would sometimes crash a few seconds after, and then sometimes it wouldn't crash. So frustrating. Then I added some kernel callbacks to monitor when there's process creation, created an ad hoc hypercall, so basically really insecure. It just would read some stuff out of some registers and act on it. And then it was a very limited because I didn't have time to rewrite it. So if I were doing it today, I would use the Bearflank hypervisor, which is an open source hypervisor developed in part. I mean, we actually fund some developers to work on it, but there's a whole bunch of folks basically trying to create a really extensible and simple way to start doing low-level research and very quickly. So why Bearflank? It's open source, so you can dig into it. It's really lightweight. It doesn't do anything it doesn't need to do, and it's very extensible. So it's like probably out of the 10,000 lines of code, it has 100% test coverage and full static analysis passing. So probably of that 10,000, very, very few of those are actually hypervisor code. So if you don't want to research how VTX works, or you don't want to read the manuals, I would say use this to focus your hypervisor. It supports 3 meg operating systems, at least by the end of the year. And the nice thing is that it's written in C++, and so you can just subclass the hypervisor and then just overwrite whatever functions you need. So if you wanted to add VPID support, something that I had to figure out on my own and kind of struggle through, there's actually an example of how you could do that. It's less than 10 lines of code to add VPID. So if I had this tool, it would save me a lot of time. If you want to trap on certain model-specific registers, so last 2015 Black Hat, they presented an attack for system management mode called Into the Memory Hole, Christopher Domas. basically allowing you to break into system management mode by writing to a certain MSR. I wrote a blog post basically saying that if you could just use a hypervisor to block that MSR, you would be able to prevent this unpreventable attack. If you're curious on how to do that, you could just grab this, which is a little bit longer. It's about 25 lines of code, and you'd be able to use this thin hypervisor with very little performance impact and prevent your system from getting owned by an unfixable vulnerability. On top of that, there's an abstraction layer called libvmi. So basically, if you are trying to monitor a process or do malware analysis where the malware is very picky about what the environment it runs in, it doesn't like seeing debuggers, it doesn't like getting touched. Basically, it provides a really simple user space API to trace, modify, or trap on the execution of software in another guest. So you can actually set up your analysis VM and then your target VM. And so you can set that up and kind of clone that however you want, and then you can do your analysis from somewhere else. It's really nice in that you can support all sorts of different hypervisors, operating systems, architectures. It integrates with recall, so you can just basically use Windows symbol tables and Windows symbol names, and it will kind of find all that stuff for you. If you're looking for some use cases, we gave it training at Troopers, which all the documents and the code and stuff is all up on GitHub. And basically, we were able to do a crack me where you have in another VM a server that requires a challenge password, and that was drawing from a whole page of memory that was all randomized. And so by doing the kind of really fast memory tracing across the VM, we were able to figure out exactly which of those 8 characters of the 4,000 or so were actually being used, and we were able to break that crack me without actually ever touching that system. SimpleVisor is another example of something that is pretty cool out there. Basically, it is very stripped down. It's done by Alex Ioesco from CrowdStrike. It's 10 lines of assembly and then 500 lines of C. It can support Windows 64-bit. If you're trying to figure out how VTX actually works and you don't want to read the manuals, or you've read them already and you don't seem to understand something, or it doesn't seem to make sense, this is a self-documenting, self-proving manual. It can load and unload while Windows is executing, so you can basically introspect on the host OS without having to do a whole bunch of more complicated VMM configuration or installing Xen, etc. Similar to that is Hyperplatform, done by Satoshi Tanda, and it's a little bit more robust and extensible for Windows-specific virtualization, but all of this stuff is kind of going to get sucked into Bearflank. They're all working on the Bearflank project now. If you want to just play in Ring 2, basically there are some skeleton kernel modules out there that allow you to just kind of hop into kernel space. Linux is a lot easier because it's you don't need to necessarily sign the drivers. Windows 10, we had to talk earlier about Windows signing for kernel code. So you either sign it by a trust certificate, use one of the hacks they talked about in the talk yesterday, or you can disable signature verification to be able to execute. If you want to play in EFI, it's actually really nice compared to BIOS because there's a reference implementation that's open source. There's another one called GNU EFI, which allows you to do development really easily. Or if you want to just introspect and kind of hook the boot process, you can download the shim loader, which was developed back in the day when Microsoft refused to unlock and boot unsigned stuff, and so Linux wouldn't boot. Shim was something that Microsoft signed that would allow you to run other operating systems. But basically what it does, if you look at the code, it just is a PE application, even signed, and then it just hooks certain functions in the boot service table, and then it passes execution something else with those callbacks registered. So it's very easy to use that as a platform for modifying the boot process on EFI. Something else that's kind of my current research is PUF library, so physically unclonable functions. They expose the manufacturing process, kind of evident in IC development, to software for device-specific responses. So basically you can request or give a challenge, and then you're going to get a device-specific return. And so that means 2 pieces of, say, memory that roll off the assembly line right next to each other will have very different characteristics. Unfortunately, they're very hardware specific. They vary with temperature and hardware age. Thus far, it's been mostly academic research and very little source code or non-commercial projects have been published. So we basically have an abstraction layer, error correction, and we're trying to get a paper published next week, basically, for a ubiquitous source of puffs that is available and accessible through software in most every system, most every laptop, basically. and it provides a very simple seal and unseal API, so you can lock data to a specific platform. So if you're doing a red team and you want to lock up some data, or you have a piece of ransomware and you want to tie it to only, hypothetically, you wanted to tie it to only that platform, you can actually do it so that even if someone were to grab that, they would be unable to recover those keys unless they're executing on the exact same system. I have no idea how we're doing on time, but I think getting close to being done. So the goal of this project was, once you have a research question that requires something further down, I wanted to make it really easy for people to hopefully figure out what features you need on the platform, or what features are even available on the platform, how you can get access to them very quickly. There's a lot of really interesting research projects in this space, and there are so many more tools now that I just didn't want to see the constant reduplication of effort. Both IRC and Twitter is a good resource for getting perspective and asking questions. The Bearflank specifically, that has like all of the hypervisor developers are just constantly emailing ridiculous questions to each other. So you're happy to jump in there. So hopefully this helped share my experiences, because I made a lot of mistakes in the past, and hopefully you guys don't make those same mistakes and don't email me with silly questions in the future. So thank you all very much for listening. My friend Thomas, he was watching the live feed, and it really improved his life. So please don't hesitate to reach out on Twitter or in person. I'll be here through the rest of the conference. So thank you. Any questions? Cool.
All right, ask some questions to show that you could follow along. I'll admit I didn't understand, but I'm not that technical. Questions? Well, you can grab Jacob in the bar later. He'll be there having a beer. So.
And then PowerPoint karaoke.
And at the PowerPoint karaoke. Probably want to talk to him before that. All right, thanks a lot, Jacob, and see you later for karaoke.
All right.
Sign up.